Now that we have looked at the different mechanisms for elimination and substitution, let's do a comparison between the four more common mechanisms. So you may have noticed that the E2 and SN2 mechanisms are favored by the same conditions. That is, we have to have a strong nucleophile slash base in the reaction. Aprotic polar solvents also helps, but it's not as critical as having a strong nucleophile or base. E1, SN1 reactions will generally be favored if we lack a strong nucleophile. So having, for example, water or an alcohol will favor E1, SN1 reactions. Protic polar solvents will also help these types of mechanisms. Now, if you have the ideal conditions for an E1 or SN1 reaction, you're going to get a mix of the two mechanisms, and usually the product formed from the SN1 reaction would be the favored product. In the case of an E2 or SN2 reaction, you might get a mix of the two, but usually you can favor one over the other a little bit more based on a few factors. So sterics, for example, if you have sterically hinder alkyl halide or sterically hinder base, you typically get E2 reactions. While having unhindered alkyl halide, you usually will have primarily SN2 reactions. Now, in the middle of those two extremes are secondary alkyl halides, so it will depend a little bit on what nucleophile or base you're using. If you have weakly basic nucleophiles, such as iodine or one of the other halogens, if you have a nitrile or the azide ion or some sort of sulfur nucleophile, usually these are strong nucleophiles that are weakly basic, so they will favor SN2 reactions. We can get E2 reactions primarily from secondary alkyl halides if we use strongly basic nucleophiles. So good examples of that are molecules that have an oxygen with a negative charge, so OR or hydroxide. Usually those will favor elimination with secondary alkyl halides. Here's a few examples to illustrate the rules we just learned. If we have an unhindered alkyl halide and an unhindered nucleophile, you're going to get primarily SN2. So here's a primary alkyl halide with a base that is basically very unhindered. Notice also we're using a good solvent for SN2, which is DMSO. It's an aprotic polar solvent. So under these conditions, we're going to get primarily SN2 with a small amount of E2 product. If we use a bulky hinder alkyl halide or base, we're going to get primarily E2. In the case of a bulky alkyl halide, like a tertiary alkyl halide, and a relatively unhindered base, we're going to get mostly decisive product from the E2 reaction. So here are the two possible alkene products. Decisive one would be the major. If we instead use a bulky base with whatever alkyl halide we're using, we're going to get primarily the anti-scisive product. So remember, this is an exception to the rule that we typically get scisive product in elimination reactions. With a bulky base, we would get the anti-scisive product. So in this case, this is the product we're going to obtain primarily. We're going to get a little bit of the SN2 product and a little bit of the scisive product as well. With secondary alkyl halides, again, it depends on what the nucleophile is. If we have a weakly basic nucleophile, such as the iodine or one of the other halogens, you're going to get primarily substitution. So since it's an SN2 mechanism, the halogen will be on the opposite side in the product as the original bromide. With a secondary alkyl halide, if we're using a strong base, then we're going to get primarily E2. So that happens with the hydroxide ion or the conjugate bases of alcohols. Those would typically give you E2. So it will be eliminating the halogen, and we're going to remove a hydrogen from the more substituted side. Or so there's two options. This methyl group has three hydrogens. This CH2 group has two hydrogens. These hydrogens are more sterically hindered, so we will get primarily the CISA product here, as shown in the product here. Very little of the SN2 product. In this question, we're going to try to predict which mechanism, SN1 or SN2, will likely be involved in the following two reactions. So in the top example, we have a secondary alkyl halide that is also benzylic, and we're using acetic acid as our reagent. In the bottom example, we have a primary alkyl halide and a reagent that is sodium methoxide, and we're also using DMF as a solvent. The top reaction here has a secondary alkyl halide that is benzylic. So that would be an alkyl halide that is somewhere in the middle in terms of sterics. But we do have a benzylic carbon where the halogen is. So that's a very weak bond. It would help us in any type of substitution reaction. And as far as the reagent we're using here, it is protic. It is a weak nucleophile. There isn't a really strong nucleophile in this reaction, so that kind of eliminates SN2. It would have to be SN1. So acetic acid would attack the carbocation that forms after the halogen is removed. So the halogen falls off, forms a carbocation, which is both secondary and benzylic. That is a fairly stable carbocation, similar to a tertiary carbocation. So it would be attacked by the acetic acid to form an acetate group, as shown here. In the bottom example, we have a primary alkyl halide. We have a base that is not hindered. And so we are going to see primarily substitution through an SN2 mechanism. The fact that the base is a pretty strong nucleophile would help us in the SN2 reaction. It would sort of eliminate the SN1 reaction. The DMF solvent would also help the SN2 reaction. In this next question, we want to predict what kind of mechanism is involved. So we have here a carbonyl with a hydroxyl group at the beta carbon. We're using a fairly strong base and ethanol. The giveaway for this reaction is the fact that there is a hydroxyl group at the beta carbon of this carbonyl. That usually leads to E1CB type mechanisms. And so that is the mechanism that is likely involved in this reaction. In this question, we want to classify the following reactions as going through one of the 5 possible mechanisms we covered in this chapter. First, we have a secondary alkyl halide that's part of a cyclopentane ring being treated with a fairly strong base, sodium methoxide, and THF. And in the second example, it's a secondary alkyl halide that is also benzylic with acetic acid and water. In the top example, we're using a strong base, so that sort of eliminates SN1 and E1 reactions. There's also no carbonyl that contains a hydroxyl group at the beta carbon, so that also eliminates E1CB. So between SN2 and E2, we want to think about what we learn about the two reactions. You might recall that for the SN2 reaction, we have to have a backside attack of the nucleophile. So it would have to get inside of the ring to eliminate this leaving group. Pentane rings are very small, so anything smaller than a cyclohexane would prevent the nucleophile from effectively being inside of the ring and doing a substitution reaction. So we're going to get primarily elimination reaction here, so we're going to see mostly E2 as we should expect. In the bottom example, we have acetic acid and water. There is no strong nucleophile, so that basically leads us to SN1 and E1, where SN1 is the primary mechanism. So here we have also a secondary alkyl halide that is benzylic. That really helps us with the SN1 and E1 reaction because we're going to form a really stable carbocation.